All right, so in this last video here, we're just going to talk a bit about, basically why the question of where a power series is continuous is actually kind of tricky, and how uniform convergence is basically the idea that we need to be able to discuss it effectively. Okay, so if we imagine, right, so let's say we're asking, we would like to know for which, let's say, for which values of x in the interval of convergence of a power series and the x to the n is this series continuous as a function of x. And it turns out that the series is basically always continuous for every value of x in the interval, with the possible exception of the endpoints. But I don't think even the endpoints, I think it's just continuous everywhere. But it's hard to show that, okay? So really what this is going to be about is kind of like examining why this is a difficult question, okay? So this is a difficult question. So importantly, I want to kind of go through what might be kind of a naive line of reasoning that a lot of people default to when they first see a question like this, okay? So naively, we might try to say this, okay? For each n, define fn of x equals the series from, k equals, let's say, 0 to n of an x to the n on the interval of convergence of the infinite series. Sorry, this is a k x to the k, of course. Right? So, of course, this function, right, each fn is a polynomial. So, of course, each fn, you could define it on all of R, okay? But we don't really care about the parts, we don't care about values of x that don't end up being in the interval of convergence of the final series, right? So the final infinite series has this interval of convergence, which might be smaller than R. So we only care to define each fn on those intervals, okay? Also, for any fixed x in the interval of convergence, the limit as n approaches infinity of fn of x is f of x, right? Where f is this overall power series, right? So if you fix any value of x, then look at the values of each fn, right? All you're doing is just adding one more term each time. And of course, by definition, that should, if the series converges, which we're saying it does because x is in the interval of convergence, if the series converges, then fn of x has to, by definition, fn of x converges to f of x, right? So these fn's are kind of like, each one is a better approximation of f of x, basically, in some sense, right? Then, so each fn is obviously continuous. So the limit of fn is continuous. This is wrong. Okay, it's wrong-headed reasoning. Okay, this is bad reasoning. It doesn't work this way, but a lot of people feel like it should, I guess. So the main substance of this little section here is I want to show you an example. This is the example the book gives too, but I'm going to show you an example of a sequence of functions. So here we have a sequence of functions, right? Fn are a sequence of functions, a sequence, not a series, right? Of course, each Fn is a sum, and the limit, of course, is this infinite series. But each Fn is a partial sum of the infinite series, right? So the Fn's, right, they form a sequence of functions. And each one of these functions basically is like a better approximation of f of x, right? So like, for example, f of x is e to the x, right? And then f1 of x is, so this is x to the n over n factorial from n equals 0 to infinity. So f1 of x would just, or sorry, f0 of x would just be 1. f1 of x would be 1 plus x. f2 of x would be 1 plus x squared over 2 factorial. f3 of x would be 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and so on. Or, well, no, not so on, sorry. Not so on. But there's, and so on this way, right? But each of these is a polynomial, okay? So they're all continuous. And of course, in this case, it so happens that f is continuous too. So we're lucky here, right? They're all continuous, but you can consider this lucky, quote unquote. You know, it's not actually lucky because since f is actually a power series, it's sort of guaranteed to be continuous anyway. But my point is that if you just think of this as a sequence of continuous functions, in general, when you have a sequence of continuous functions, if they converge to something, it's not automatic. If they converge in this sense of like, you know, for each fixed value of x, fn of x converges to f of x. If they converge, if the functions converge to f in that sense, the limiting function is not guaranteed to be continuous, okay? So let's look at an example of that. So this is example 8. All right. Not power series. So these functions are not power series, but the point is that they form a sequence of continuous functions whose limit is not continuous, okay? So define fn of x to be 1 minus absolute value of x to the n on negative 1, 1. Okay? So the graphs are like, you know, this is f1. Let's see. Oops. Let's make this a little bit more symmetric. This would be f2, and you know, as you can see, with each, actually these are supposed to be the same value. Let's make it really, oops. Really bowed inwards here. So this would be F3. And so as you can see, it kind of bows inward more and more and more. So fn of x, the limit as n approaches infinity of fn of x is 0 for all x not equal to 0 in -1, 1. But the limit as n approaches infinity of fn of x equals 1 for x equals 0. Okay? So as you can see, so basically at every point except exactly when x equals 0, eventually when n gets big enough, fn of x will, as n gets bigger and bigger, fn of that value of x will approach 0. But they all kind of approach 0 at different rates. Like as you get closer and closer to x equals 0, fn approaches 0 slower and slower and slower and slower. So no matter how big n is, there's always some values of x where fn is like close to 1, right? So not where x equals 0. So values of x that are non-zero but close to x equals 0, where fn is close to 1. Okay, so the limit, right? The limit function, otherwise known as the pointwise limit in this case. And we call it the pointwise limit because it's just the function you get by taking, sorry, I should try to spell this or try to write this a bit better. Pointwise, okay? All right. W's are hard. So this is the pointwise limit because what we're doing is we're basically fixing a value of x. We like fix a value of x and then look at what happens to fn of x as n approaches infinity, right? So we do that for each value of x and we get a new value which becomes the value of our limit function, okay? The sequence fn is f of x equals 0 for x in -1, 1 without the point 0, and 1 if x equals 0. Okay? So that's clearly f is discontinuous, right? So the point is a sequence of continuous functions can converge pointwise to a continuous limit. Okay. So, right, I mean, you can tell that each fn is continuous, but the limit is actually discontinuous. So that's why we can't just say that a power series is automatically continuous just because each partial sum is continuous, right? No. The logic there is not valid. We need something stronger, okay? So the question would be, when can we say that a sequence of continuous functions converges to a continuous limit? That's what we need uniform convergence for. So uniform convergence is a stronger form of convergence if a sequence of continuous functions converges uniformly, the limit must be continuous. Okay, so that we're going to formulate that property in the next lecture, but we need something more than just, right, our version of convergence right now is just like at each value of x separately on its own, fn of x converges to f of x. That's the version of continuous convergence that we're talking about, right? But there's actually a stronger condition you can formulate, which is saying basically that like all the fn of x's for all the different values of x, fn of x approaches f of x like kind of all at the same rate or something like that. Okay, so that would be one way of thinking about it, but I'm not going to formulate it now. That's for the next lecture. But to also kind of point in that direction, I want to return back to the end. So the end of, I believe it's the end of section 22. Yeah. Section 3.22. They make this definition. So let S be a subset of R. Let C of S be the set of continuous bounded functions on S. Okay, so the elements of C of S are actually functions, right? Then define D of FG for F and G in C of S. The distance, we're gonna turn it into a metric space. So the distance between two bounded functions, two bounded continuous functions on S, is going to be the supremum of the difference of their values, or the distance between their values, for all x in S. Okay, so we're going to basically, the idea is it's like the farthest distance between F and G on S, between values of F and G on S, right? So, there might be places in S where F is close to G in value, and then there are other places where F is farther from G in value. And whatever the supremum of all of these, differences in value is, that's the distance between F and G as two functions, okay? So this turns C of S into a metric space. I'm not going to prove that right now. In fact, this is another great example of something that might be healthy for you guys to try to prove on your own, just to verify the axioms of a metric space for this purported metric. But you can trust me when I say that this does turn C of S into a metric space. And actually, now we can think of, right, if we go back to our example, we can think of, Fn, the sequence Fn is like a sequence in, so Fn is a sequence in C, this is supposed to be a C, C of -1, 1, right? So there's like a kind of a technical issue, but well, okay. Let's actually restrict the domain of Fn and F by deleting the point 0. Okay. So yeah. So okay. In the previous example, redefine Fn, to exclude 0, to exclude x equals 0 from the domain. Okay, and and the same for the limit f, right? So if we exclude 0 from the domain, then f of x equals 0 for x in the domain of f, because now we've deleted the point. Remember, because f itself was just 0 for all of these points except for x equals 0. But now we've deleted x equals 0 from the domain. So f of x is just 0, right? So the domain of f, remember, now that we've deleted this point, it's -1, 1 without 0, right? So fn is in C of -1, 1. Well, okay, let me just set s for convenience to be -1, 1 without the point 0. Okay. Then fn is in C of s for all n, as is f. However, the distance from fn to f, I claim, is 1 for all n. Okay, so fn does not converge to f in C of s as a metric space. Okay, even though, so f, now that we deleted the point 0 from the domain of f actually becomes continuous. So, I mean, this no longer serves as a counterexample in the sense that, like, now the limit, all the functions are continuous in the sequence, and the limit is also continuous. But the problem is that the sequence still does not actually converge to the limit in this metric space. It only converges in a different sense, which is pointwise. Okay, so this f, you can only call we haven't actually defined what it means for a sequence of functions to converge to another function, basically. Okay, we actually haven't made that definition at all. So they're basically, what I'm saying is that there are like multiple different competing ways that you might try to define convergence for a sequence of functions. One would be just to look at what happens to the sequence of functions at any fixed value of x, and then just do that for like every different value of x. That's what we call pointwise convergence. And so what I'm saying is that fn does converge to f pointwise. It converges in that sense, but there's a different sense of convergence in which sense this sequence does not converge to f, right? And this is actually an example of that, okay? So we already have a definition of convergence for arbitrary metric spaces. And according to that definition, this sequence doesn't actually converge to f. So that's kind of a strange thing. Okay, and if you don't, so, just to verify this, look at, so I'm going to draw fn. So now we're excluding the point 0, right? And we also kind of exclude, we exclude these endpoints over here, but that doesn't matter. So here's fn, right? This is fn, and then this is f, right? So, at all these small values of x, so for small x, the absolute value of fn of x minus f of x gets arbitrarily close to 1. This is true for any n, right? No matter how big n is, there's still a little area right around 0 where the value of fn shoots up to 1, basically, right? So it's this counterintuitive phenomenon where basically, if you only pay attention to a single value of x, no matter how small that value of x is, eventually fn of x will converge to 0. But if you allow yourself to look at all the values of x at the same time, no matter how big n is, there's always some value of x that's small enough that the value of fn of x is actually quite large. So yeah, let me just write that down. So I'm going to make a cut here while I write that. So, okay, yeah. So what you can see is if we fix a value of x, then no matter how small it is after we fix it, if we let n get larger and larger, the value of fn of x will eventually approach 0. But if we fix some value of n, no matter how big it was, no matter how big the value of n is, once it's fixed, you can find a value of x that's small enough so that fn of x is actually close to 1, okay? So that's the strange sort of, it's something that's hard to wrap your head around at first. And this is very important for you to get comfortable with as fast as possible. This basic phenomenon is like a huge theme for like the rest of the class pretty much, okay? So I would say definitely pay attention to this example. And that's why, right? So the supremum, right? The supremum here, for any fixed n, right, the supremum of this difference, right, I mean, this is actually just equal to 0. So the supremum here is just 1 for any fixed n, right, no matter how big n is. This supremum is always 1. So the distance between fn and f is actually always 1, even though fn converges pointwise to f. Fn does not converge in the sense of sequences in a metric space. It does not converge to f. And that's, this is, ends up being equivalent to Fn not converging uniformly. The only reason I did this whole business of deleting 0 from the domain was so that actually f would end up being an element of C of S. You could actually there are several other modifications you can make. So instead of deleting 0, if I could have done something different from the book and actually said and set C of S to just be the set of bounded functions on S, and then this would still make sense if C of S was just the set of bounded functions that weren't necessarily continuous. And then this whole discussion could have been done without deleting the point 0, because f would have actually been in C of S even though it wasn't continuous. So that was one thing you could have done. Another thing that I could have done was just basically, I could have shown that even with C of S defined as only continuous functions, I could have shown that the sequence Fn is not Cauchy in C of S, okay? So that's actually another thing that I'll just write down. So Fn is not Cauchy in C of S either. I'm not going to show that because it's a bit of a pain, but it's not, I mean, well, it's not that bad, but yeah, I just don't want to spend the time right now. But this is not Cauchy, so that's also another reason we shouldn't expect it to converge as a sequence in this metric space, okay? Okay, so that's all for this video, and that concludes this lecture. Then in the next lecture, we'll actually define uniform convergence, and we'll show that uniformly convergent sequences of continuous functions are continuous, and so on. We'll continue from there. So see you then.